Welcome to this video discussing Basic Intelligent Resilient Framework, or IRF. This is an HPE technology that allows you to stack multiple switches into one logical switch. In this video, we will discuss some of the basics of IRF. Please refer to other videos on HPE's website for discussions on advanced IRF concepts. Physical devices are added to the IRF stack, also known as the IRF virtual device, and also known as an IRF system, and these physical devices are called member devices. So in this example, we have two physical switches that have been added to an IRF system or an IRF stack, once again also known as an IRF virtual device. An IRF system consists of at least two physical switches identified by member numbers. The member numbers need to be unique. So in this example, we have two devices. Member 1 is the master IRF device, and member 2 is the slave or standby IRF device. There are two roles in an IRF system. We have what's called the master device, and there's always a single master device in an IRF virtual device or IRF system. And then we have one or more slave devices or standby devices. The master device manages the IRF system. The standby devices or slave devices in the IRF system operate as backups for the master device. If the master device fails, one of the standby devices is elected as the new master. In this example, the master device has a member ID of 1, but the master device doesn't necessarily have to be member 1. The master device is once again in control of the IRF system and provides various features, including the control plane, the management plane, and other features. As an example, if you connect to the console of a slave device and use the command display current config, you're viewing the config of the master device, not the slave device. One of the ways to think of IRF is similar to a chassis-based switch. In a chassis-based switch, you have a management module. This is the brain or the module in charge of the physical chassis-based switch. Then you have some modules that provide physical connectivity. The master device in an IRF system is logically the management module. So in other words, it's the brain of the IRF system. The standby devices or slaves are logically line cards in a chassis-based switch. So on the left-hand side, we have a chassis-based switch. It's a single switch with a single management module and multiple interface modules providing physical connectivity. They don't have their own active control and management functions, but are reliant on the management module. On the left-hand side, we have multiple physical switches with one master and two standby switches. Logically, this acts as a chassis-based switch with cables connecting the different modules together. Unlike a chassis-based switch, however, in this example, if the management module fails, the switch goes down, whereas here, when the master fails, one of the slave devices can transition to the master function, and the IRF system or IRF stack can continue working. The standby or slave devices also have a copy of the configuration file, and those are stored locally on their flash. So if the master fails, they do have a copy of the configuration, and the IRF system can continue functioning. So how is the master device elected in an IRF system? It's not based on the member number. In this example, the master device has a member ID of 1, but it doesn't have to. Member 2 could have been the master. So the master is determined as follows. It's done via an election process where the current master wins, even if a new member has a higher priority. So let's assume for the moment that this switch had a priority of 30 and is currently the master, and a new switch is added to the topology and has a priority of 32. The current master will stay the master, and this switch member 3 would become a slave or standby device. The default priority is 1, but when you create a new IRF system, the highest priority wins. So when initially configuring an IRF system or virtual device, this first step is skipped because there is no current master. Then it's done on priority. So if we had a new IRF system consisting of 3 switches, let's say, for instance, that there are multiple cables here, this switch had a priority of, let's say, 30, this switch had a priority of, let's say, 20, and this switch had a priority of, let's say, 10, this switch would become the master switch because it has the highest priority. Now, if the first criteria cannot be used because there is no current master and the priorities are the same, let's say, for example, the priority of these 2 switches is set to 1, which is the default, then the longest uptime is used to determine who the master device is. The precision interval for the system uptime is 10 minutes, and this information is transmitted in IRF hello messages sent between the switches. If that can't be used to determine who the master is, let's say both switches come up within a few seconds of each other, then the lowest MAC address is used to determine who the master unit in the IRF system is. It's not good practice to use longest uptime and lowest MAC address when determining the master in the IRF system, so it's better to set the priority on your devices when forming a new IRF system. Now, there's a separate video in this series that demonstrates the various options here. So you'll see an example where the current master wins, an example where the highest priority wins, an example where the longest uptime wins, and an example where the lowest MAC address wins. Once again, you want to use this criteria rather than these when creating a new IRF system. And also be aware that the current master will win. So once again, even though you add an additional device to the IRF system that might have a higher priority, the priorities are in the range 1 to 32. So let's say, for example, that you have the priority of this switch set to 30, this switch set to 20, and a new switch joins the IRF system or IRF stack with a higher priority. This switch will remain the master because it's the current master. However, if it was a new IRF system, then this switch would become the master because it has the highest priority. And what happens when the master goes down? Let's assume for the moment that this device on the left is the master. It has a priority of, let's say, 32. This device on the right is the standby device or slave device and has a priority of 30. These ports are connected as IRF ports, and this is an IRF system. What happens when the master device goes down? So when the master device goes down, the standby device will become the new master because it's the only device available. Let's say you rebooted the master, so it wasn't a physical failure, it was just a reboot. When the master goes down, the slave becomes the new master device. When the master comes back again and rejoins the IRF system, it will now rejoin as a standby device and not as a master device. This slave device or standby device became the master when the master went down. So it's currently the master when this previous master device joins the IRF system. So the current master wins. So because the switch on the right is currently the master, when the switch on the left went down, it will remain as the master device and the roles will change in this example. So now member 2 is the master device and member 1 is the standby device. Another important concept when discussing IRF is the concept of physical IRF ports versus logical IRF ports. Physical ports are ports such as 10 gigabit 1049 or 10 gigabit 1050. These are the actual physical ports used to connect 2 switches or multiple switches in an IRF system. The logical IRF port is not a physical port but a configuration option that dedicates specific physical interfaces to the IRF function. So these physical interfaces or physical ports cannot be used for traditional link aggregation or for traditional connections to other devices. These ports are now dedicated to IRF and can be seen as a logical extension of the backplane between these 2 physical switches. So logically, in a similar way to a chassis-based switch having a management module and then, for example, Ethernet modules inserted and then connected via the backplane of the switch. In the same way here, we have a master connecting to standby switches, and the physical backplane connection is made using these physical interfaces. So as an analogy, and it's only an analogy, these physical interfaces have been associated with the logical IRF port in the same way that physical interfaces would be associated with a link aggregation port, or in ComWare terms, a BAG port, bridge aggregation port. IRF does not use standard link aggregation for the connection between the members in an IRF system, but as an analogy, the same concept is true. Physical interfaces are associated with a logical interface and are now dedicated to that function. An IRF port allows you to bond one or multiple physical interfaces to the logical IRF port for greater throughput. So as an example, you could connect 2 cables between these 2 switches, as I've done in this example, or you could add additional links to provide greater throughput between the switches. Now, these physical interfaces start with a number such as 2 in this diagram, or 1. That number is the member number in the IRF unit. By default, it's 1. So if we have 2 physical switches set to factory defaults, the port numbers on both of these switches would be 1049 and 1050. However, one of the first things you need to do when setting up IRF is change the member numbers. You can only have one member in the IRF system with a member ID of 1. So this switch has its member number changed to 2. When you reboot the switch, the port numbers change, starting with the member number. So they change to 2049 or 2050. When you have 3 members in the IRF system, the port numbers would start with 1 for member 1, or 2 for member 2, as in this example, or 3 for member 3. Once again, when the switches are shipped, the member numbers would all be 1, but you can only have one member in the IRF system with a member number of 1. So you would change the member numbers, reboot the switches, and the interface numbers would change to the following. You don't have to cable the physical interfaces with the same numbers. So in this example, we've got 47 connected to 47 and 48 connected to 48. That's not a strict requirement. It's only done in this example to make it simple and easy to read. So 49 doesn't have to be connected to 49 and 50 to 50. We could have, for example, have connected 2050 to 3049, and 49 could have been connected to 50. The physical interface numbers do not need to be the same. They can be different or they can be the same. However, with logical IRF ports, they have to be different. So in this first example, we've got IRF logical port 1/1 connecting to IRF logical port 2/1. The first number is once again the member number, so member 1 and member 2, and the second number is the IRF port. However, you cannot connect IRF port 1 to IRF port 1, so this is an incorrect configuration. You need to connect IRF port 1 to IRF port 2, as in this second example. So we've got IRF member 1 connecting to IRF member 2, but port 1 is connected to port 2. That is the correct way to configure the IRF stack or IRF system. In this example, we've extended the topology by adding a third member, and this is using what's called a daisy chain topology. Member 1 is connected to member 2, and member 2 is connected to member 3, but there's no connection between member 1 and member 3. Notice how the logical IRF ports are connected to each other. So the physical interfaces could be the same numbers, 10 gigabit 1049 to 10 gigabit 2049, but what's important is the logical IRF ports. IRF port member 1, port 1, is connected to IRF member 2, port 2, which is correct. In this example, we have IRF member 2, port 1, connected to IRF member 3, port 2, which is also correct. 1 has to connect to 2, and by the same token, 2 has to connect to 1. These are the logical IRF ports. You cannot connect 1 to 1 or 2 to 2. That's not supported. So ensure when you configure your IRF logical ports that you always configure IRF port 1 to IRF port 2 and vice versa. In this example, we're using what's called a ring topology, which provides an additional level of redundancy when compared to a daisy chain topology. If both of these physical links went down as an example, there's still connectivity between the members in the IRF system. But in this example, notice how the IRF logical ports are connected. We have IRF member 1, so member 1, port 1, is connected to IRF member 2 on port 2. IRF member 1, port 2, is connected to IRF member 3 on port 1. So port 2 is connected to port 1, and port 1 is connected to port 2. For this connection, the logical IRF port 2/1, so member 2 port 1, is connected to IRF member 3, so member 3 port 2. Never connect IRF port 1 to IRF port 1 or IRF port 2 to IRF port 2. There are demonstrations in the Advanced IRF video series showing you what happens if you did that. In the examples thus far, we've used 2 physical IRF ports between the IRF members. But do you need more than 1 physical IRF port? So could you connect member 1 to member 2 using only a single physical cable? The answer is yes, you can. There is no explicit requirement to have at least 2 ports. 1 port is sufficient. It's more cost-effective to use a single cable, and this configuration is supported, but you need to be aware of the issues if you have a cable break. If that cable goes down, the IRF system is split. You then have 2 IRF members that may believe that they're both the master in the IRF system. They cannot communicate with each other because the IRF port is down, and they may both determine that they are the master device, which causes a lot of conflicts in the network as both these devices are using the same MAC address. HPE have a technology called multi-active detection, or MAD, that helps you resolve this issue, and we'll discuss that briefly in a moment. But to try and mitigate this issue, you may want to use at least 2 cables. So if one of the cables goes down, the IRF system in the second example can still continue as a single system because the 2 IRF members are able to communicate with one another using the additional cable. You may also have a situation where traffic is being received on member 1, and for whatever reason, the traffic is being sent to a device that's connected to member 2. So in this case, we have user data traversing the IRF ports. So in this example, you may want to add additional links to the members in the IRF system to increase the performance when traffic goes across the IRF system. So be aware, it's possible to use only a single cable between the IRF members. So you could use only a single 10 gigabit port. But there's some disadvantages to doing that, including the examples discussed here. If that port goes down, you've lost connectivity between your IRF members. In this example, we've got 2 physical IRF ports, which allows us to send more traffic between hosts on the left-hand side to hosts on the right-hand side. A single port may become a bottleneck for the sending of user data. Multi-active detection, or MAD, is a technology that allows for IRF recovery when the ports linking switches in the IRF system go down. So in this example, we have 2 switches in the IRF system or IRF stack, and the links between both switches have gone down. We now have a situation where the IRF system is split, and this is often called a split brain. Both switches would believe that they are the master device in their local IRF system that's split from the other device. They cannot see each other using the IRF port, so they now believe that they are the master device. This causes confusion in the network, as multiple physical devices are stating that they are the single IRF device. All member devices in the IRF virtual system use the same MAC address, the same IP addresses, and other configuration settings, so this causes a lot of confusion in the network. So to stop this confusion, MAD will take one of the switches offline, so only a single master device remains in the network. This device on the right is taken out of the network by shutting its ports down. So all ports on the switch are shut down except the physical IRF ports on the switch. In the advanced IRF videos available on the HP website, we will talk about LECP MAD, BFD MAD, and ARP MAD, which are 3 different implementations of MAD to stop a split brain scenario. Now, with regard to software versions, it's recommended that devices in the IRF system or IRF stack run the same operating system version. IRF does support an auto software upgrade mechanism in certain cases. When a new IRF member is added to the IRF system, it does not need to have the same software version as the virtual IRF device. It only needs to have what is called a compatible version. When the new device is added to the IRF stack, it will compare its software version to that of the master switch. If the versions are not consistent, it will automatically download the boot file from the master, reboot using the new version, and join the IRF stack again. However, be aware that if the device does not support this feature, you will need to manually update the software version of new members before adding the member to the IRF system. That concludes this video discussing the basics of IRF. Please refer to the HP website for additional videos, including demonstrations and videos about advanced IRF topics. Thank you for watching.